Hello and welcome back to Math Concepts. We are going to continue our discussion of basic probability. In this video we are going to look at something called the complement rule. Now, in certain examples you'll find that there are actually a ton of ways to meet your criteria for success. Okay, for example, I might be rolling two die and looking for a sum of at least 2. No, actually, no, that's not a great example. Let's look at a sum of at least 3. Okay, I want the sum to be at least 3. Okay, well, there's a ton of ways to do that. I could get a sum of 3, I could get a sum of 4, I could get a sum of 5, or anything up to 12. Okay, so I could find all of these probabilities individually and then add them up, or what I could do is look at the probability of not getting at least 3. And the only other option is getting a 2. Okay, and the probability of getting a 2 is 1 out of 36. So the probability of getting at least 3 is 35 out of 36. Okay, so with the complement rule, you're looking at kind of the opposite and then subtracting. So let's look at some examples of finding probability using the complement rule. Okay, so the key idea from this video is you should be able to find probability using the complement rule. Now your hint, look for the words at least or at most. And that should indicate to you that the complement rule could help. Okay, so for example, let's look here, right? 2 dice are tossed. What is the probability of getting a sum of at most 11? So in this case we want 11 or less. Okay, now there's a bunch of ways to do that. You could get any sum from 2 through 11 inclusive, and it would meet your success condition. So we could break this down into all those separate events and apply the addition rule, but there's a simpler way to do it. Okay, we're looking at the probability of getting a 12. Now we know when we toss 2 dice, there's 36 possible outcomes. There's only one way to get a 12. So the probability that we can get less than or equal to 11 is 35 out of 36, right? Because there's only one way not to get that. Okay, in other words, what we do is we do 1 minus this probability that we just figured out. Okay. Let's look at another example down here. Okay, we're going to toss a coin 5 times, and we want to know the probability of getting at least 1 heads. Okay, now the complement of getting at least 1 heads is no heads at all, or all tails. Okay, notice we see the keywords at least 1. Okay, now the thing to note here is that there is only one way to get all tails, right? Every single toss has to come up tails. Getting at least 1 heads, there's tons of ways to do that. You could get all heads. You could get 4 out of the 5 being heads. You could get 3 out of the 5, 2 out of the 5, 1 out of the 5. So the complement rule lets us focus our attention and cut down the number of cases that we have to look at. Now, I need to think here about my sample space. I'm not going to write it out. I'm going to use the counting principles to figure out the size of the sample space for this experiment. I am tossing the coin 5 times, so that's 5 stages. I have to think about how many ways each stage can be completed. It's pretty easy to figure out that there's only 2 ways to do each stage. First toss, it's going to come up heads or tails, 2 possibilities. The same for the subsequent 4 tosses. Okay, so the sample space has 32 elements in the sample space. Now the probability of all tails would be 1 out of 32, right? We just discussed there's one way to do this. The probability of at least 1 heads would be 31 out of 32. Okay, so there's 32 possibilities in all. Our reasoning says that one of the 32 does not meet our criteria. Therefore, the other 31 do meet our criteria. So the probability of getting at least 1 head is 31 out of 32. So great use of the complement rule right there. Let's try one more. Okay, we're rolling a die 7 times. What is the probability of at least 2 6s? Okay, so once again we see at least. Okay, now the complement for this actually has 2 parts. Okay, there you could roll 1 6, you could roll no 6s. Now, you're talking about at least 2 6s, and you're rolling the die 7 times, so there's way more ways to get at least 2 than its opposite. Okay? So the initial event that we're going to try to find the probability of has so many ways to be completed, right? You have 2 6s, 3 6s, 4 6s, 5 6s, 6 6s, and 7 6s. So there's 6 ways to be successful. We'd have to find the probability of each one individually and add them. But there's only 2 ways to be unsuccessful. So let's look at that, because that's simpler. Okay. Once again, we need to look at the size of the sample space. It's a 7-stage experiment. We're rolling the die 7 times. Each stage can come up any of 6 ways, right? I'm rolling a single die and I'm doing that 7 times. Okay, I'm just going to call that 6 power 7. If I use my calculator, I can give that to you. I guess it's not huge. 279,936 ways to do this. Okay. Now, I got to think a little bit about ways to get not a 6. No 6s at all. Now, it's not quite as easy as the last example. Okay? In the last example, you're talking about either heads or tails. So if we wanted no heads, in other words, all tails, there was only one way to do that. If you're not getting any 6s, okay, you still have a bunch of other things that you could get. In fact, we're going to roll that die 7 times. 1, 2, 3, 4, 5, 6, 7. You're talking about the die coming up one of the other 5 numbers. Okay. So that's 5 power 7. And we can use our calculator here. 78,125 possibilities. So this is the total sample space. So the probability of no 6s is 78,125 out of 279,936. Okay. Now let's look at the probability of exactly 1 6. Okay, you got 7 spots. We're going to pick one of them, and that's where the 6 is going to be. So, 7 spots, choose one. We're going to use a combination. I don't really need to do that, but I want to be fancy. And then, now this is the tricky part here, the remaining 6 spots can be anything. Okay, so I'm going to pick one of the spots. That's got to be a 6. I got 7 choices. The remaining 6 spots are completely random, just not a 6. 1, 2, 3, 4, 5, 6, 7. Okay, if I do this computation, I'm getting 109,375. Okay. This isn't really the probability, this is kind of scratch work. So the probability of 1 6 is 109,375 out of 279,936. So down here we can figure out the probability of 2 or more 6s. Okay, so we're going to do 1 minus the probability of getting just 1. Which we just found. And we also have to take away the possibility that you don't get any at all. Okay. And we could do that computation, and that will tell us the probability of getting at least 2 6s. So that's a more complicated example of the complement rule, but we're still using the complement rule.